All right, let's do some heat engine example problems. These problems are a little bit wordy, so pay attention. Problem number 1. I'm heating a house with a heat pump, keeping it at a constant temperature of 25 degrees C, even though it's 12 degrees C outside. The coefficient of performance heating mode for the pump under these conditions is 4.7. The house is leaking heat at a rate of 400 watts. How much power does the heat pump need to consume to keep the house at temperature? And how much heat would it need to consume if it were an ideal Carnot heat pump? All right, so basically what we're given a coefficient of performance, and we're given how much heat is exiting the house. All right, so we have a power exiting, right? Power, I'll call it P sub E, and that was 400 watts, right? So in other words, there's a heat leaving our house in every second of 400 joules. So every second 400 joules leaves the house. All right, which means we need to put 400 joules back into the house. All right, so our Carnot engine basically, we have some hot reservoir, T hot, and we have a cold reservoir, T cold, and we're putting work in to our heat pump to pull heat from the cold reservoir, Q cold, and deposit some Q hot into the hot reservoir. All right? So the coefficient of performance for heating, we are given that, right? It's 4.7. But what is the coefficient of performance equal to? Right? Whenever we talk about efficiency or coefficient of performance, it's what we want divided by what we put in to get it. So for a heat pump, what we want is we want to deposit heat into the house. Q hot. That's how much we want to put in. All right? And what do we put in to get it? We put in work. So if I know the coefficient of performance, all right, and I know how much heat I want to put in 1 second, that's my 400 joules, I can find how much work I have to put into my heat engine in 1 second. So the work I have to do is just going to be, I solve this equation, it's going to be Q hot divided by the coefficient of performance, right? So the work in 1 second is 400 joules divided by the coefficient of performance, which is 4.7. All right, so that's the work in 1 second. So to get the constant power, work per second, I just have to divide this by second. So the power I have to put into my pump is just going to be 400 watts, 400 joules per second divided by 4.7. And you can pull out your calculator and figure out what that's equal to. Here, I've got a calculator right here. So 400 divided by 4.7. So it turns out, even though 400 watts are leaving my house, I can keep it, I can make up for that by putting only 85.1 watts into my heat pump, and the heat pump pulls the rest of the heat it needs from outside, from the cold outside. All right? So that's the great thing about a heat pump, right? If I had an electric heater or a gas heater, whatever energy I expended goes right into my house, right? If I put in 400 watts of electrical power, I get 400 watts of heating in my house. But a heat pump leverages the power. That 85.1 watts that I put into my heater, all right, that ends up into my house, but in the process it pulls some additional heat from outside. All right, that's the great thing about a heat pump. All right, so we needed 85.1 watts. What if this were an ideal Carnot heat pump? All right, so an ideal Carnot heat pump, right, no friction, everything works reversibly. How well could we do in the theoretical limit? All right, well, our coefficient of performance, again, coefficient of performance is Q hot, the heat that goes into our house, divided by the work we put in to get it. All right, so once again, our heat pump takes in some work, deposits Q hot, it pulls Q cold, all right, up. All right, so what is work? We can think of work in terms of Q hot and Q cold. Q hot is just going to be the work plus the heat we pull in from the outside. Right? So work is just equal to Q hot minus Q cold. All right? So the coefficient of performance, we could also write it as this, Q hot divided by the work, which is Q hot minus Q cold. All right? So Q hot is the sum of the work we put in plus what's pulled in from the outside, which means that work is Q hot minus the heat we pulled in from the outside. All right? So there's the coefficient of performance written just in terms of Q. What is the coefficient of performance for an ideal Carnot heat pump? All right, so when we did a Carnot engine or a Carnot refrigerator or a Carnot heat pump, the trick to this is when you go through the derivation, you find out that you can write the Q's in terms of the temperatures times something that cancels out on above and below, all right, in the numerator and the denominator. So for a Carnot, without actually going through the full derivation, for a Carnot refrigerator, heat pump, or refrigerator, if you write your coefficient of performance as a ratio of things involving heats, for a Carnot device, we can replace the Q's with temperatures, T hot over T hot minus T cold. All right, this is for, once again, this is the coefficient of performance for heating mode. For cooling mode, the thing we want is Q cold, so we replace that with Q cold. But for heating mode, this is the coefficient of performance. All right, so I don't know if you can see my calculator on the screen here, but what I'm going to do is I'm just going to plug in, what was T hot? We said that we're keeping our, let's go up and look again. We're keeping our house at 25 degrees C, it's 12 degrees outside. So Q hot is, we have to do it in Kelvin, right? So T hot is 25 degrees plus 273.15 to convert it to Kelvin. The cold temperature is going to be, we said it's 12 degrees plus 273.15, convert from Kelvin. So if I take T hot divided by T hot minus T cold, all right, that turns out to be a coefficient of performance of 22.9. All right, so the power we would need for my heat pump, we decided that was just the 400 watts that's leaving divided by the coefficient of performance. But for an ideal Carnot heat pump, that would be 22.9. So now we only need 400 divided by 22.9 watts, so 17.5. So if we had an ideal Carnot heat pump operating between those two temperatures, we would only need 17.5 watts. Now notice, as it gets colder and colder outside, as this approaches absolute zero, the coefficient of performance for even our ideal Carnot heat pump goes to 1. All right, so if you throw in any additional losses, friction, heat leaking through your pipes and stuff, it turns out that heat pumps work really well if the temperature difference between the outside and the inside is small. When it starts to get really big, the heat pumps aren't as effective. All right, problem number 2. I design an impractical heat engine. I start with my gas at a pressure PA with the piston fully extended, giving my cylinder its largest possible volume, VA. Then I compress the gas in the cylinder at constant pressure to its minimum volume, VB. Then I add heat to the system, increasing the pressure at constant volume. Finally, I do an adiabatic expansion to return to the starting point. In order to return to the starting point, what should the maximum pressure in the cycle be, and what is the efficiency of the engine? All right, so once again, let's draw a PV diagram. It's going to look something like this. All right, I start at some volume VA and some pressure PA. And I said what I first did is I compressed my gas at constant pressure to a volume VB. All right, constant pressure. So this is pressure PA. Then at constant volume, I increase the pressure. And then I do an adiabatic process to get back to my starting point. Now, if I start here and I do an adiabatic expansion back to volume A, there's no guarantee that I end up at the same pressure I started with. So I have to get this up to the correct pressure. If I want this to be a cyclic thing, all right, with just these three processes, I need to make sure I start my adiabatic process at the correct pressure so that I end up at the correct pressure once I get to the final volume. So I want to know what that pressure is. Let's call this point A, B, and C, and I want to know the pressure at C. That's the first thing I want to know. The next thing I want to know is what's the efficiency of this engine, all right? So first of all, the pressure. How do I find the pressure at C? Well, this is an adiabatic process, right? So pressure C times volume C to the gamma must equal pressure A, volume A to the gamma, all right? And of course, volume C is the same as volume B because we did a constant volume expansion to get up there. So because it's an adiabatic process, I can use this equation. The volume at C is also the same thing as the volume at B. So I can solve this and find that the pressure at C is just the pressure at A times VA over VB to the gamma. And volume at A is bigger than volume of B, which means the pressure up there has to be higher. That's just what we expected. So there we have the equation to find what pressure we need to go up to so that when we do our adiabatic expansion, we come back to our starting point. Okay, now the next question is, what is the efficiency of this heat engine? So this is a heat engine. Efficiency is, right, what we want divided by what we put in to get it, which is work, divided by Q hot. All right, and your book likes to put little absolute value signs here to remind you that Q hot and Q cold are always positive, even though sometimes they flow out of the cylinder, whereas previously Q is always positive for heat flowing into our gas. All right, but when we talk about heat engines, Q hot and Q cold are always positive. All right, so if I can find the work done by this engine, now I could do the work, I could find the work by, look, I do negative work as I go across here, well, positive work on the cylinder, which means negative work on, the cylinder's doing negative work on, you know, my drivetrain or whatever it's driving, right? No work is done here, and then I can find the work done by the adiabatic expansion, and that is one way I could find the work, all right? But there's another way I could find the work, right? Because how does a heat engine work? I've got some hot reservoir, I've got some cold reservoir, I've got my heat pump. Heat flows from the hot reservoir to the cold reservoir, in the process giving some of that energy off as work. So here's Q hot, here's Q cold, and I say, oh, well, work is just going to be the difference between Q hot and Q cold. Right? So basically some heat flows in, some of it flows out as work, and some of it is exhausted to the cold reservoir. So I could do the work integral to find the work here and find the work here, but I've got to find Q hot anyway. If I find Q cold, I can find the work by just taking the difference between Q hot and Q cold, right? So I can write my efficiency as Q hot minus Q cold divided by Q hot. So if I can find Q hot and Q cold, I can get the efficiency. Okay, what is Q hot and what is Q cold? Q hot is the sum of all the heat that enters the engine, and Q cold is the sum of all the heat coming out of the engine. So where does heat enter my engine? Well, on the adiabatic process, there's no heat. Q is equal to 0. So if the adiabatic thing isn't part of Q hot or Q cold. Here, I'm starting at a big volume, and at constant pressure, I'm going to a smaller volume. So imagine I have a piston that's holding up some weight, right? So it's at constant pressure. How do I get the piston to go to a smaller volume? I have to lower the temperature of the gas by pulling heat out. So in this part of the process, when I go from A to B, all right, heat comes out and temperature drops. All right, so that's heat flowing out, so that's part of Q cold. All right, here I've got a piston. I'm not changing the volume, but I'm increasing the pressure. To increase the pressure, that means that heat needs to come in to increase the temperature, which means heat in, temperature increases. All right, so here is heat flowing in, that's Q hot. Here is heat flowing out, this is Q cold. So this is going to be Q hot right here, and I can find Q cold right here. All right, although heat is flowing out, so the Q I calculate will be negative. So if I calculate the heat going from A to B, all right, Q cold is the absolute value of that. Now, if there were more processes, I'd have to take all the ones where heat flows in, and that's all part of it. They add them all together to get Q hot. Take all the places where heat's flowing out and add them together to get Q cold. But for this engine, I've just got two processes. So Q cold is when I go from A to B, and Q hot is when I go from B to C. All right, so let's look at going from A to B. What is heat when I go from A to B? It's constant pressure at pressure A. So when I go from A to B, it's constant pressure. It's going to be at pressure PA, and I'm going to go from volume VA to volume VB. All right, that's A to B. How do I find what Q is? Well, I use my first law of thermodynamics. The change in internal energy is equal to Q plus work. All right? What is the change in internal energy? So let's first solve this. So Q is going to be equal to the change in internal energy minus the work. All right? The change in internal energy is always NCV delta T, and the work is minus the integral of P dV. Right? So for this particular process, how do I find the change in temperature? All right, well, I have my ideal gas law. PV is equal to nRT. All right, this is a constant pressure process, so pressure doesn't change. So if volume changes by a factor of 2, that means temperature has to change by a factor of 2. If volume changes by a factor of 4. The temperature has to change by a factor of 4. All right? So if I take the derivative of this, right, if I do some change, right, let's write it this way. So the pressure is constant if I have some initial volume. That's equal to nRT initial temperature. All right? And if I have some final volume and some final temperature, all right, to find the temperature difference, I can just solve these, right? Temperature initial is PV initial over nR. All right? Temperature final is just going to be PV final over nR. So the change in temperature is just going to be pressure. Of course, the pressure is PA, right? PA over nR times V final minus V initial, all right? And of course, my final and initial volumes are, my final volume is VB, and my initial volume is VA. All right, and if I look at this, VB is smaller than VA, so the temperature is going to go down. I'm going to have a negative temperature change, which means I have a negative change in internal energy. That's what we said, right? In order for my piston at constant pressure to go down, I needed to pull heat out of it and make it colder, so the temperature goes down. So there's my dt, all right? What about this part? What about the integral of PdV? Well, at constant pressure, the pressure comes out, and then it's just the integral of dV, all right? So the work, so P dV, then it's just going to equal the pressure, PA, and then I integrate the volume, it's just going to be the change in volume. It's going to be VB minus VA. All right, so putting this all together, the heat is NCV delta T, so NCV, and delta T is PA over NR VB minus VA, all right? And then my negative work, you know, minus W, is just this here. So we add in PA VB minus VA, all right? Okay, we can simplify that, but first let's look at this. The change in internal energy is negative, right? And it should be, right? And we said, oh, this is negative. The work done on our gas, if our gas is compressing, the work done on the gas, right, is going to be positive. And if we look at this term right here is actually negative, but that's because, right, we were supposed to have a negative in front of it. So it turns out the work done is positive. It seems like things are going the right way, so we have some confidence in our answer. So let's write this down. This is the heat that flows into our gas from A to B, and it turns out to be negative because it's actually heat flowing out. So let me rewrite this nicely. So Q from A to B is equal to, we can combine these, right? So I've got an N, these N's will cancel out. I have a PA VB minus VA in front of everything, so I can just write this as CV over R plus 1 PA VB minus VA. All right, so that's what we get. That's Q from A to B, and we decided that that's the only place in our cycle where heat leaves the system, so that must be Q cold, except Q cold is the absolute value of this, right? Because this is going to be negative. It's heat flowing out of the system. So Q cold, then, is just negative of this. So CV over R plus 1 PA, and I'll swap my minus sign here to make this negative. VA minus VB. And Q cold and Q hot should always be positive, right? Because they're absolute values. And VA is bigger than VB, so I get something positive. There is Q cold. I have now found Q cold. Next, I need to find V hot. Let's look back at our diagram. Q hot is what happens when I go from B to C at constant volume. All right? So let's go from B to C. B to C is a constant volume. All right? And we're going to start at pressure A, right? Because the pressure at B is the same as the pressure at A. And we're going to go to pressure C. All right? And we found out what pressure C was earlier. It's just PA VA of VB to the gamma. So this is equal to PA times VA over VB to the gamma. All right? Once again, how do I find Q? I use the the first law of thermodynamics, which says the change in internal energy is Q plus work, which means that Q is change in internal energy minus work. All right? The change in internal energy is NCV delta T. All right, I need to find what delta T is again. All right, and how do I do it? Once again, ideal gas law. PV is equal to nRT. In this case, the volume is constant, so if I change the pressure, the temperature has to change accordingly, right? So the change in pressure times volume has to equal nR change in temperature. As you recall earlier, when looking at like the adiabatic gas law derivation, we said if everything's changing, I have to do like a chain rule thing here. But since the volume is constant, I can just write this as change in pressure times volume is equal to nR change in temperature. So our change in temperature is just going to be delta P times the volume, and the volume, of course, is volume B, right, divided by N times R. So the change in internal energy then is just going to be NCV times delta P VB over NR. The N's cancel, so this is just CV over R VB. And what's the change in pressure? The change in pressure, we're going from pressure A to pressure C, but that's just, pressure C is just pressure A, so we can pull out the pressure A. Alright, and pressure C is just pressure A times VA over VB to the gamma. And then we're going to subtract off our initial pressure, which was just pressure A, so I put a 1 there. Now let me write that more legibly. So the change in internal energy is CV over R times volume at B, pressure at A, times the ratio of our volumes, VA over VB, to the gamma, minus 1. Alright? So there's the change in internal energy. Now I need to find what minus work is. Alright? Wait a minute. It's a constant volume process, isn't it? If the volume doesn't change, sorry, I forgot to put the V up here. It's a constant volume process. If there's no change in volume, there's no work done. Which means that's our change in internal energy. That's also Q from B to C, but that's also Q hot. Alright? And Q hot is heat flowing in, so I don't need to change the sign of it to get Q hot. So now I've got Q hot. Alright, so I've got Q cold, I've got Q hot. My efficiency is just equal to work over Q hot, what we put in, or what we want divided by what we put in to get it. And work is just Q hot minus Q cold. Alright, so that's that, and I can write this as 1 minus Q cold over Q hot. So my efficiency is just going to be 1 minus Q cold. Where's Q cold? Q cold is this, CV over R plus 1. So CV over R plus 1, all multiplied by PA VA minus VB. PA VA minus VB. There's Q cold, and now I divide by Q hot, which is right up here, which is CV over R times VB PA, alright, times VA over VB to the gamma minus 1. Alright, so there's our efficiency. Notice that the PA's cancel out. That's kind of nice. Alright, and let's multiply top and bottom by R over CV. So this is going to look like now 1 plus R over CV VA minus VB divided by 1 times VB VA over VB to the gamma minus 1. Okay. Alright, we can simplify this still by multiplying top and bottom by 1 over VB. So this is going to be 1 minus 1 plus R over CV. Then if I divide top and bottom by VB, this is going to be VA over VB minus 1, all divided by VA over VB to the gamma minus 1. Okay. There we have the efficiency, but I'm going to simplify this a little bit more. I've got 1 plus R over CV, so let's think about that. 1 plus R over CV, that's just CV over CV plus R over CV, and that's just CV plus R over CV. CV plus R is CP, that's CP over CV, so that's just equal to gamma. Alright, so this is just then 1 minus gamma VA over VB minus 1 divided by VA over VB to the gamma minus 1. And there is our efficiency. Alright, so hopefully that helps you with the homework.